Light a candle. Go ahead. Just a regular candle, the kind you buy at the grocery store. Watch the flame for a second. Now blow it out. Where did the wax go? No, really. Think about that. You started with a candle that weighed, let us say, 6 ounces. You burned it for a while. Now it is shorter. You weigh it again, and it is lighter. Something left. Something escaped. But you did not see anything leave, did you? You saw a flame. You felt heat. Maybe you smelled something. But no little chunks of wax went flying off into the room. So where the hell did it go? That question, that simple, annoying little question about a candle, is the same question you are really asking when you ask what cremation does to a body. And the answer is far stranger and more beautiful than most people ever bother to find out. So let us start with the candle. Let us start with something so ordinary that nobody ever thinks about it. And we will stay with it for a while, because everything we need to understand about cremation is already happening in that little flame on your kitchen table. A candle is made of wax. Wax is made of molecules. And what are those molecules? They are long chains of carbon atoms with hydrogen atoms hanging off the sides. That is all wax is. Carbon and hydrogen holding hands in long rows, like children walking in a line on a school trip. The carbon is the backbone, usually about 20 or 25 atoms in a chain. The hydrogen atoms are clinging on, 2 or 3 per carbon, and these molecules just sit there in the wax, solid and still, packed together neatly, doing nothing interesting at all, until you bring in a match. Now, what does the match do? It does something very specific. It gets the temperature of a small region of wax high enough that the wax melts, and then high enough that the liquid wax starts to vaporize. The liquid crawls up the wick by capillary action, the same trick that makes a paper towel soak up a spill, and at the top of the wick the heat is enough to turn the liquid wax into vapor. Now that vapor mixes with the oxygen in the air around it, and you have fuel and oxygen in the same place, at the same time at a temperature where they can react, and that is when fire happens. Fire is not a thing. I want you to hear that clearly. Fire is not an object. It is not a substance. The ancient Greeks thought fire was one of the 4 elements, alongside earth, water, and air. They thought it was a fundamental ingredient of the universe. They were wrong. Fire is not a thing. You cannot put fire in a jar. Not really. Fire is a process. It is a chemical reaction that you can see. It is what it looks like when atoms rearrange themselves very quickly and release energy while doing it. That glow, that flicker, that dancing yellow shape above the wick, that is the visible signature of atoms breaking old partnerships and forming new ones. Nothing more, nothing less. And the yellow color, by the way, that comes from tiny particles of soot, unburned carbon, that get heated to incandescence. Little specks of carbon glowing white hot like the filament in an old light bulb. So what is actually happening inside the flame? The carbon atoms in the wax vapor meet the oxygen molecules in the air. Oxygen floats around as pairs, 2 oxygen atoms bonded together. And when a carbon atom meets one of those oxygen pairs at the right temperature, something wonderful happens. The carbon lets go of its hydrogen neighbors. The oxygen lets go of its oxygen partner. And the carbon grabs onto 2 oxygen atoms instead. 1 on each side. Carbon dioxide. 1 carbon, 2 oxygens. A new molecule. A gas. And it drifts away, rising up in the warm current of air above the flame. Meanwhile, the hydrogen atoms that were hanging onto the carbon, they find oxygen too. 2 hydrogens grab 1 oxygen. Water. Actual water. Every candle flame is making water. Tiny invisible wisps of water vapor, rising up and mixing into the air in your room. You are sitting there watching a candle, and it is quietly manufacturing water right in front of you. If you hold a cold glass over a candle flame, you will see the water condense on the glass, little droplets forming. Proof. The candle is making water. And look at the flame more closely. Look at its structure. There is a dark region, right at the base, close to the wick. That dark zone is where the wax vapor has just left the wick, but has not mixed with enough oxygen yet to burn. It is rich in fuel, but starved of air. Above that there is a bright yellow region, the main body of the flame. That is where the combustion is happening, but incompletely, where tiny particles of carbon soot form and glow white hot, giving the flame its color. And at the very edges, especially near the top, there is a thinner, almost invisible blue zone. That is where combustion is most complete, where the fuel meets plenty of oxygen and burns cleanly. Different parts of the same flame, different stages of the same chemical reaction, all happening within an inch of space. a whole chemical factory running in a volume no bigger than your thumb. So the wax did not disappear, not a single atom of it vanished. Every carbon atom that was in that wax is now floating around your room as part of a carbon dioxide molecule. Every hydrogen atom is now part of a water molecule. The wax became air, became gas, became invisible, but every atom is still here, somewhere, doing something new. And by the way, the total mass of carbon dioxide and water vapor that left the flame is actually heavier than the wax you started with, because the wax combined with oxygen from the air, and that oxygen has mass too. The stuff floating around your room after the candle burns weighs more than the candle did. It is just invisible, so you do not notice. Now let me tell you who figured this out, because the story is a good one. For centuries, people thought that when something burned, a mysterious substance called phlogiston was released. You burned a piece of wood, and the phlogiston escaped. That was the theory. It explained why things got lighter when they burned. The phlogiston was leaving. Elegant, simple, totally wrong. In the 1770s, a French chemist named Antoine Lavoisier did something radical. He weighed things before burning and after burning, but he weighed everything, including the gases. He built elaborate sealed glass apparatus, heated metals inside closed vessels, captured every wisp of gas, weighed every gram of residue. He was meticulous in a way that nobody before him had been. And what did he find? The total mass did not change. Not by a grain. The stuff that seemed to disappear during burning had actually combined with something from the air. He identified that something as oxygen, and he gave it that name, from the Greek for acid maker. And just like that, phlogiston was dead, and modern chemistry was born, all because somebody had the discipline to weigh the air. Lavoisier paid dearly for being a scientist in revolutionary France. He was also a tax collector, which made him politically unpopular. In 1794, during the Reign of Terror, he was sent to the guillotine. The mathematician Joseph Louis Lagrange reportedly said afterward that it took only an instant to cut off that head, and 100 years may not produce another like it. The atoms that made up Lavoisier's body, the man who first proved that atoms are conserved in chemical reactions, those atoms were themselves conserved. They went on, they became soil and air and water and eventually parts of other living things. His own discovery applied to his own flesh as it applies to all flesh. That principle, that matter is neither created nor destroyed in a chemical reaction, is the law of conservation of mass, and it is central to everything we are about to discuss. Hold on to it. Let me ask you the next question. What was the heat? Where did the warmth come from? You felt it on your hand when you held it near the flame. The room got a tiny bit warmer, energy came out, but from where? Here is the secret. The atoms in the wax, the carbon and hydrogen, they were bonded to each other, and those bonds have energy associated with them. The specific way the atoms were connected, that arrangement stores energy. When the atoms rearrange, when carbon joins oxygen instead of hydrogen, the new bonds are stronger. They are more stable. The new arrangement is at a lower energy level. And the difference, the energy gap between the old arrangement and the new one, that difference has to go somewhere. It comes out as heat and light. Think of it like a ball sitting on a ledge halfway up a hill. The ball is not doing anything, but it has potential energy because of where it is. Give it a nudge, a little push to get it over the lip, and it rolls down to the bottom. It speeds up, the potential energy turns into motion. The ball does not create energy from nothing. It releases energy it already had by changing position. The atoms in fire are doing the same thing. They are falling into more comfortable arrangements. That little nudge, the match, is the activation energy. And the energy they release on the way down, that is the heat that warms your hands. That is the light that dances in the flame. The match does not supply the energy for the fire. The wax does. The match just gives the molecules the initial kick they need to get the reaction started. So fire is atoms rearranging into more stable patterns and releasing stored energy in the process. Every fire you have ever seen, a candle, a campfire, a forest fire, a gas stove, is the same process at different scales. Atoms finding new partners and releasing stored energy as they do. Good, now we know what fire is. Now let us talk about you. You sitting there listening to this, what are you made of? You know the answer in a general way. Atoms. But which ones? If I took you apart, atom by atom, and sorted them into little piles on a table, what would I get? The biggest pile by far would be oxygen. About 65% of your body by mass is oxygen. Most of it is locked up in water molecules because you are mostly water. About 60% water by weight. The next pile would be carbon, about 18%. Carbon is the backbone of every organic molecule in your body. Your proteins, your fats, your DNA, the membranes of every cell, the sugars in your blood, all of it built on frameworks of carbon atoms. Then hydrogen, about 10%. Then nitrogen, about 3%, critical for your amino acids in your genetic code. Then a smaller pile of calcium, about 1.5%, most of it in your bones and teeth, packed into dense mineral crystals. Then phosphorus, about 1%, part of your bones, part of every molecule of ATP that powers your cells, and part of the backbone of your DNA. Then even smaller piles, potassium, sulfur, sodium, chlorine, magnesium, and then traces. Tiny, tiny amounts of iron, zinc, copper, manganese, iodine, selenium, and a few dozen other elements in quantities so small you would need a sensitive scale to weigh the pile, and yet those trace amounts matter enormously. The iron in your blood, about 4 grams total, just enough to make a small nail. That iron is what lets your hemoglobin carry oxygen from your lungs to your tissues. Without it, you suffocate from the inside. The iodine in your thyroid, barely 1/5 of a gram, regulates your entire metabolism. The zinc in your enzymes, the copper in your electron transport chains, the cobalt at the center of every molecule of vitamin B12, all of them essential, all of them present in amounts so small they barely register on a scale. You are a trace element machine. Your life depends on micrograms of rare metals scattered through your tissues in exactly the right places. But here is what matters most for our story. Every single one of those atoms, every oxygen, every carbon, every calcium atom in your bones, every iron atom in your blood, not one of them was made by your body. Not one of them was created for you. Every atom in you was forged somewhere else a long time ago and has been wandering through the universe ever since, passing through stars and rocks and oceans and other living things, until one day it happened to end up in the food you ate, or the water you drank, or the air you breathed, and your body grabbed it and stuck it into a molecule somewhere. You did not create any of your atoms. You assembled yourself from a parts bin that the universe has been stocking for billions of years. Now, what happens when you die and your body is cremated? That is the question. And now you have enough pieces to understand the answer, because cremation is fire. And you already know what fire does. A modern cremation chamber, which the industry calls a retort, operates at temperatures between about 1400 and 1800 degrees Fahrenheit. That is roughly 760 to 980 degrees Celsius. These are serious temperatures. For comparison, your kitchen oven maxes out at maybe 500 degrees Fahrenheit. A wood fire in your fireplace might hit 1100. But a cremation retort is significantly hotter than either. The chamber is lined with fire-resistant refractory bricks, and the heat comes from gas burners, usually natural gas, directed at the body from above and from the sides. The process takes about 2 to 3 hours for an average adult. And during those hours, several distinct things happen in stages. First, the water boils off. Remember, your body is about 60% water. At 212 degrees Fahrenheit, that water starts turning to steam. In the first phase of cremation, an enormous amount of water vapor leaves the body. Pure steam, just water molecules escaping into the air. This alone accounts for a significant fraction of your mass. After the water is driven off, the soft tissues begin to combust. Your skin, your muscles, your organs, your fat. All of it is made of carbon-based molecules combined with hydrogen, oxygen, nitrogen, and smaller amounts of other elements. At the temperatures in the retort, in the presence of abundant oxygen from the air supply, those molecules come apart. The chemical bonds that hold them together break, and the atoms rearrange, just like the atoms in candle wax, into more stable combinations. The carbon in your tissues meets oxygen. Carbon dioxide forms and rises away as gas. The hydrogen meets oxygen. Water vapor forms and rises away. The nitrogen in your proteins, most of it ends up as nitrogen gas, which is what the atmosphere is mostly made of anyway, or as small amounts of nitrogen oxides. The sulfur from your amino acids, particularly from cysteine and methionine, combines with oxygen to form sulfur dioxide. Fat burns vigorously. If you think about it, fat is chemically similar to wax. It is long hydrocarbon chains with lots of stored energy. A body with more fat tissue will actually burn hotter and faster. The cremation operator sometimes has to manage the airflow to prevent the temperature from spiking too high when the fat combustion is at its peak. All of these combustion products are gases. They float up and out through the exhaust system of the crematorium and into the outside air. In modern facilities, those gases pass through filtration and scrubbing systems to remove particulates and certain pollutants before being released. But the carbon dioxide and water vapor pass through. They enter the atmosphere. Your soft tissue does not turn into ash. I want to be very clear about that because most people have the wrong picture in their heads. They imagine the body sort of drying out and crumbling into the gray powder that gets returned in the urn. That is not what happens. The soft tissue burns, it oxidizes, it turns to gas. The atoms that made up your muscles and your brain and your liver and your kidneys leave the chamber as invisible molecules mixed into the atmosphere. They are gone from the room, but they are not gone from the earth. Oh, they are in the air. So what is the stuff in the earth? That bones, or rather what is left of bones after you heat them to that temperature for 2 to 3 hours. Your bones are a composite material like fiberglass or reinforced concrete. They have an organic component, mostly the protein collagen, which gives them flexibility and toughness, and a mineral component, mostly a crystalline substance called hydroxyapatite, which is built from calcium, phosphorus, and oxygen, with some hydroxide groups mixed in. The mineral part gives bones their hardness and rigidity. During cremation, the collagen burns away. It is a protein, it is organic, it combusts just like the rest of the soft tissue, but the mineral portion, the hydroxyapatite, does not burn. Why? Because it is already fully oxidized. The calcium is already bonded to oxygen and phosphorus in its most stable arrangement. There is no lower energy state for it to fall into. It is already at the bottom of the energy hill. Fire cannot push it any further down, but the extreme heat does transform the bones. It drives off the water incorporated into the crystal structure. It causes the mineral to become brittle, chalky, fragile. After the cremation process, what remains in the chamber are bone fragments, dry and pale, resembling rough chunks of calcium mineral. These fragments are then processed mechanically, usually in a device called a cremulator, which grinds them into a fine uniform powder. That powder, that is what goes into the urn. So the ashes, as people call them, are not ashes at all in the chemistry sense. Real ash from a wood fire is mostly potassium carbonate and calcium carbonate, the mineral residues of plant material. What you get back from a cremation is ground bone mineral. Calcium phosphate mainly, with smaller amounts of sodium, potassium, magnesium, and trace metals that were incorporated into the bone during life. Strontium, for instance. Lead, sometimes depending on environmental exposure. And those trace metals tell a story if you know how to read them. The strontium in your bones reflects the geology of the places where your food was grown, because strontium substitutes for calcium in the bone crystal, and the ratio of strontium to calcium varies by region. Archaeologists use this trick to trace the migrations of ancient peoples by measuring strontium isotope ratios in their bones. The bone mineral is a kind of archive. Even after cremation, even ground to powder, it retains a chemical fingerprint of where and how that person lived. Then there are the non-biological materials, dental fillings, surgical pins, plates, screws, artificial joints, hip replacements and knee replacements made of titanium and cobalt chromium alloys, pacemakers which actually have to be removed before cremation because they contain batteries that can explode in the heat. These metals do not burn, they sit in the chamber after the combustion is done, warped or discolored by the heat, but chemically intact. The cremation operator removes them with a magnet or by hand before the bone fragments are processed. In some facilities, the recovered metals are recycled. And how much of you is that? The bone mineral, I mean. By weight, the cremated remains of an average adult come to about 5 to 7 pounds. Your body weighed, let us say, 150 or 170 pounds. So the remains in the urn are roughly 3 to 4% of your original body mass. The rest, 96 to 97%, left as gas, flew away, joined the atmosphere. Let me say that differently because I want it to sink in. 96% of you by weight goes into the sky during cremation, as carbon dioxide, as water vapor, as nitrogen gas, as small amounts of sulfur compounds. The vast, overwhelming majority of what was you becomes air. Now, here is where it starts to get really interesting. Let us follow those atoms after they leave the chamber. And now, let us track them, because they do not just sit in the atmosphere doing nothing. They go places, they participate, they get used again. Take the carbon dioxide molecules. The ones that contain carbon atoms that used to be part of your muscle fibers or your brain cells or the lining of your stomach, those molecules mix into the atmosphere. They drift. Wind carries them. Within days, they are spread across the region. Within weeks, they are spread across the hemisphere. Within a year or so, they are distributed around the entire globe. Some of those carbon dioxide molecules will be absorbed by the ocean. The ocean is an enormous carbon sink. Carbon dioxide dissolves in seawater, reacts with water to form carbonic acid and bicarbonate ions, and enters the vast oceanic carbon cycle that turns over on timescales of centuries to millennia. But some of them will be grabbed by a plant. A tree somewhere, maybe a mile away, maybe on another continent, will pull one of those carbon dioxide molecules out of the air during photosynthesis. Using sunlight as the energy source, the plant will crack the molecule apart, strip away the oxygen, keep the carbon, and stitch it into a sugar molecule, a glucose, 6 carbons in a ring with hydrogen and oxygen hanging off, and the plant will use that sugar to build cellulose for its cell walls, or starch for energy storage, or lignin for structural strength. Your carbon becomes part of a tree. Maybe a caterpillar eats a leaf from that tree. Now your carbon is in the caterpillar. A bird eats the caterpillar. Now your carbon is in the bird. Now the bird exhales, and some of that carbon leaves as carbon dioxide again. Or the bird dies, and bacteria decompose its body, releasing the carbon, and the cycle starts over and over. The water molecules that form from your hydrogen atoms, they join the water cycle. They might evaporate from a lake surface within hours, and they might fall as rain within a few days. They might end up in a river, then the ocean, then a cloud, then rain again in India or Brazil or Norway. They might be drunk by a child on another continent. They might be taken up by the roots of a sunflower. They might freeze into a snowflake and land on a mountain peak and sit in a glacier for 10,000 years. But eventually they move. Water never stays still for long on this planet. The nitrogen goes back into the atmosphere where it came from. Nitrogen makes up 78% of the air you breathe right now. The nitrogen atoms that were part of your amino acids and your DNA bases rejoin that enormous atmospheric pool. Eventually, over months or years or decades, soil bacteria will fix some of those nitrogen atoms into ammonia or nitrate, forms that plants can absorb through their roots. Plants will build new amino acids from them. Those amino acids might end up in a grain of wheat that someone bakes into bread, and the nitrogen is inside a person again. Every atom that leaves the cremation chamber goes somewhere. Every atom continues. The fire did not destroy a single one. It could not. No chemical process can destroy an atom. It takes nuclear reactions to change one element into another. Cremation is not a nuclear reaction. It is chemistry. It is just atoms changing dance partners. And this is the thing that surprises people most if they really sit with it. When we say somebody is gone, when we say the body is gone after cremation, we mean the pattern is gone. The extraordinary arrangement that made those atoms into a specific person. The precise organization of trillions upon trillions of molecules into cells, cells into tissues, tissues into organs, organs into a system that could walk and talk and think and laugh. That is what the fire dismantles. The atoms themselves are indestructible by fire. They were here long before that person was born. They will be here long after. Let me push this further, because it applies to you right now while you are still alive. You think of your body as a fixed thing, as solid, as you, but your body is replacing its atoms constantly. You eat food, you drink water, you breathe air. New atoms come in, get built into your tissues, hang around for a while, and then get swapped out and expelled. Your body is like a fountain. The shape stays the same, but the water flowing through it changes every moment. Different tissues replace their atoms at different rates. The cells lining your intestine replace themselves every 3 to 5 days. Your red blood cells last about 120 days before they are broken down and their components recycled. Your outer skin cells turn over every 2 to 3 weeks. Your skeleton replaces most of its mineral content over a period of about 10 years. Some molecules in your brain, the really stable lipid components of myelin sheaths, might persist for decades. But on average, most of the atoms in your body right now were not there 7 to 10 years ago. You are not the same collection of atoms you were a decade back. So in a very real sense, cremation just does quickly what life was already doing slowly. The atoms cycle through you, and then they cycle out. Fire speeds up the exit, but the exit was always happening. You have been losing atoms and gaining new ones every single day of your life. And here is a thought that might shake you a little. Every time you exhale, you are sending carbon atoms into the atmosphere, atoms that were recently part of your living tissue. Your body metabolized a sugar molecule, burned it for energy, exactly the same oxidation reaction as a candle flame, just slower and controlled by enzymes instead of raw heat. And the carbon left your body as carbon dioxide in your breath. You are combusting all the time. Right now, as you sit there, your cells are burning glucose, stripping electrons from carbon, passing them along a chain of molecular machinery, and exhaling the spent carbon as gas. Breathing is slow, careful, enzymatically controlled fire. Every breath you take is a little cremation, a few trillion carbon atoms released from your body, returning to the air. The process is identical. The scale is different, the speed is different, but the chemistry is the same. And the food you eat? That is you recruiting replacement atoms. The carbon in your dinner was pulled out of the atmosphere by a plant using sunlight and built into sugars and proteins and fats. You eat the plant, or you eat something that ate the plant, and your body disassembles those molecules, salvages the carbon and nitrogen and everything else, and builds them into your own structures. You are constantly rebuilding yourself out of the atmosphere through the intermediary of other living things. Life is a loop. Atoms come in, atoms go out, and you are the pattern that persists while the material flows through. I want to talk about energy for another moment, because people sometimes ask, what about the energy? Is something lost when a person is cremated? The total energy is conserved, just like the atoms. This is another ironclad law, the conservation of energy, the first law of thermodynamics. The chemical energy that was stored in the bonds of the body's molecules gets released as heat during combustion. That heat warms the air in the chamber, it warms the bricks. It exits through the exhaust, it radiates from the building into the surrounding air. It becomes part of the thermal energy of the environment. It spreads out, diffuses, becomes less and less concentrated. And this spreading, this dispersal, is the part that breaks your heart if you think about it long enough. It's because the energy does not just spread, it becomes less useful as it spreads. But this is entropy, the second law of thermodynamics. Energy tends to go from concentrated, ordered forms to dispersed, disordered forms. A lump of coal has concentrated chemical energy. Burn it, and that energy becomes heat spread across a room, warming the air by a tiny, even amount. The total energy is the same, but the usefulness of that energy, its ability to do work, to drive processes, to maintain structure, has decreased. You cannot unscramble the egg. You cannot gather the waste heat from a room and reassemble it into a lump of coal. Living systems fight entropy every second. Your body takes disordered raw materials, food, water, air, and assembles them into extraordinarily organized structures, proteins folded into precise three-dimensional shapes, DNA coiled and packed into chromosomes with billions of base pairs in exact sequence. Cell membranes maintaining different chemical environments on each side. This all requires constant energy input. You eat to get that energy. You metabolize it, use it to maintain your structure and run your processes and release waste heat into the environment. You are, thermodynamically speaking, a machine that creates local pockets of order at the expense of greater disorder in your surroundings. Death is what happens when that machine stops running. And cremation is the rapid, thorough completion of what death began. Without the constant energy input and active maintenance of a living metabolism, the complex structures fall apart. Cremation accelerates the process from weeks or months of slow decomposition to 2 or 3 hours of combustion. But the thermodynamics story is the same either way. The organized energy stored in your body's molecules disperses into the environment as heat. Entropy increases. The local order that was you dissolves into the general disorder of the surroundings. And if you were not cremated, if your body were buried instead, the same thing happens, just much more slowly and with different intermediaries. Bacteria and fungi do the work instead of fire. They break down your proteins, your fats, your carbohydrates, using enzymatic chemistry rather than combustion. They metabolize your molecules for their own energy needs, releasing carbon dioxide and water and nitrogen compounds as they go. The end products are exactly the same. The atoms end up in the same places. The difference is the timeline and the route. Cremation takes hours. Decomposition in soil takes months. to years, depending on conditions. But the final atomic accounting is identical. Every carbon atom ends up as carbon dioxide. Every hydrogen atom ends up as water. Every nitrogen atom returns to the soil or the air. The conservation of mass holds, whether the process takes 2 hours or 2 decades. And here is the melancholy beauty of it. Nothing is lost in the accounting sense. Every atom is still here, every joule of energy is still here. But the organization is lost, the structure is gone. The particular arrangement that made you, that arrangement is what does not survive. And information, once scrambled, is staggeringly difficult to reassemble. It is like shuffling a deck of cards. All 52 cards are still there after you shuffle. Nothing is missing, but the specific order they were in is gone. And the odds of shuffling back to that exact order are 1 in about 8 times 10 to the 67th power. That is an 8 followed by 67 zeros, a number so large that if every person on Earth shuffled a deck once per second from the beginning of the universe until now, you would not come close to exhausting the possibilities. You would not even make a dent in them. The number of possible arrangements is that large. And a human body is not 52 cards. It is roughly 7 billion atoms. The number of possible arrangements of those atoms is so incomprehensibly vast that the card shuffling analogy understates the problem by a factor that has no name in any human language. The same principle applies to the atoms of a cremated body. Buddy, they are all out there, scattered but present. Reassembling them into the original person would require not just gathering the right atoms, but positioning each one exactly where it was, trillions upon trillions of them, in the right molecules, in the right cells, in the right three-dimensional arrangement, with every protein folded correctly and every membrane intact. The probability of that happening by chance is so negligibly small that it functionally rounds to zero, not improbable, impossible, for all practical purposes. Let me tell you something else about the temperatures, because the numbers reveal something about scale that I find illuminating. The cremation chamber reaches 1400 to 1800 degrees Fahrenheit. That is hot by our standards, devastating to biological material. But by the standards of the universe, these are almost cool temperatures. The surface of the sun is about 10,000 degrees Fahrenheit. The interior of the sun reaches about 27 million degrees. Inside a supernova explosion, temperatures hit billions of degrees. At those stellar temperatures, even atoms come apart. Electrons get stripped away from their nuclei. You get plasma, a soup of free nuclei and free electrons. And at the temperatures in the cores of massive stars, nuclei themselves collide and fuse into heavier elements. That is where your carbon came from. That is where the calcium in your bones was made. Helium nuclei smashed together at hundreds of millions of degrees inside a dying star, fusing into carbon, oxygen, neon, magnesium, silicon, and on up through the periodic table, all the way to iron. And elements heavier than iron, the gold and uranium and lead, those were forged in the actual explosion of the supernova itself, in the few seconds of cataclysmic energy release as the star tore itself apart. Cremation cannot do any of that. It operates in the realm of chemistry, not nuclear physics. It can break molecular bonds, the electromagnetic connections between atoms, but it cannot touch the nuclei. It cannot crack a carbon nucleus. It cannot split an oxygen atom. Those nuclei are held together by the strong nuclear force, which is about 100 times more powerful than the electromagnetic force of nuclear distances. You would need temperatures of millions or billions of degrees or the focused energy of a particle accelerator to break atoms apart. A furnace, even a very hot one, is laughably far from that threshold. This means something remarkable. The calcium atoms in the bone powder in the urn, those specific calcium nuclei, were assembled inside a star. Each one, every single calcium nucleus in those remains was built by nuclear fusion under conditions so extreme that nothing on Earth can replicate them outside of a laboratory. Those calcium nuclei survived the supernova that scattered them. They survived 4.5 billion years of geological churning on this planet. They survived being part of a living body for decades. And they survived the cremation fire without a scratch. The fire is just not in the same league as the forces that hold a nucleus together. It is like throwing a tennis ball at a battleship. So, at the atomic level, cremation is gentle. It is a surface-level rearrangement. The atoms do not even notice. If atoms could have experiences, which they cannot, they would find cremation utterly unremarkable. Just another chemical reaction in a career spanning billions of years of transformations. Think about what one of your carbon atoms has been through. That atom was forged in a star maybe 6 or 8 billion years ago in the triple alpha process, where 3 helium nuclei slammed together under unimaginable pressure and temperature to create a single carbon nucleus. The star burned for millions of years more, then it ran out of fuel in its core and collapsed. The outer layers rebounded off the dense core and blew outward in a supernova explosion that for a few weeks outshone its entire home galaxy. The carbon atom was flung into space at thousands of miles per second. It drifted in an interstellar cloud for millions of years, part of a thin fog of gas and dust between the stars. Then gravity gathered that cloud together. It began to collapse. It spun. A disk formed. At the center, a new star ignited, our sun, and in the disk around it, rocky planets coalesced from the dust and gas. The carbon atom ended up in the Earth about 4.5 billion years ago. Maybe it spent its first few 100 million years locked in a rock deep underground in a carbonate mineral, going nowhere. Then volcanic activity melted the rock, and the carbon was released as carbon dioxide into the early atmosphere. A primitive single-celled organism, one of the first photosynthesizers, pulled that carbon dioxide out of the air and built it into an organic molecule. And from that point on, for billions of years, the carbon cycled through organisms and the atmosphere and the ocean, over and over, endlessly. It was in algae, in fish, in soil bacteria, in ferns, in dinosaurs, in trees, in the air, in the sea, in coal deposits, back in the air, in grass, in a cow, in a glass of milk, and then in you. You used it for maybe 50 or 60 years, and the cremation fire sends it back out as carbon dioxide to continue the journey it has been on for longer than the Earth has existed. Against that biography, being part of you was one brief chapter. Important to you, but to the atom it was just another stop along the way. There is a calculation people sometimes do, a rough back-of-the-envelope estimate, about how many atoms from a specific historical person you might be breathing right now. The atmosphere contains roughly 10 to the 44th molecules. Each breath you take pulls in about 10 to the 22nd molecules. And each person who ever lived exhaled over a lifetime roughly 10 to the 29th molecules of carbon dioxide, plus even more water molecules. Run the numbers and what you find is startling. Every single breath you take contains, on average, at least one molecule that was once exhaled by any specific person who lived more than a few hundred years ago. Not approximately. At least one. Probably several. The atoms get around, they mix, they diffuse, they do not belong to anyone. Michael Faraday, the great English experimenter, gave a series of Christmas lectures for young people at the Royal Institution in London back in 1860. The topic he chose was the chemical history of a candle. He spent 6 lectures on it, 6 full lectures for children about a candle. And he never ran out of things to say, because a candle, once you start looking at it carefully, contains within it an enormous amount of physics and chemistry. Faraday showed his audience that you could understand combustion, the nature of gases, chemical reactions, the composition of the atmosphere, even respiration and the chemistry of life, all from watching a candle burn. He told them that there is no better door by which you can enter into the study of natural philosophy than by considering the physical phenomena of a candle. I think cremation is the same kind of door. It sounds morbid. People wince when you bring it up at a dinner table. But once you look at it with the eyes of physics, it opens up into something vast. It connects to the conservation laws. It connects to thermodynamics and entropy. It connects to the carbon and water and nitrogen cycles. It connects to stellar nucleosynthesis and the origin of elements. It connects to the deepest, most fundamental question about what it means to be a physical being in a universe where every atom is interchangeable and every arrangement is temporary. The fire does not end anything, not in the atomic sense. It transforms, it rearranges, it disperses, it returns. The atoms that were a person go back to being available, back to the great churning, restless, endlessly recycling inventory of matter on this planet. And some of those atoms, statistically, inevitably, over the years and centuries that follow, will end up in other living things. In plants, in animals, in other people. Not in a mystical sense, in a straightforward, trackable chemical sense. So when somebody asks me, what does cremation do to your atoms, the answer is clear and strange. It sets them free. Not spiritually, physically. The atoms were locked into an extraordinarily complex arrangement, held there by chemical bonds that were constantly maintained by the energy-consuming machinery of life. The fire breaks those bonds. The atoms form simpler, more stable molecules, gases, and they leave, they rejoin the atmosphere, the ocean, the soil. They go back to the great common pool of matter that has been cycling on this planet for 4.5 billion years. Nothing is lost, the books balance. Every atom accounted for. Every joule of energy accounted for. Lavoisier would be satisfied. The conservation laws hold as they always do, without exception, without failure, without mercy. But the pattern, the magnificent, improbable, unrepeatable pattern that was a human being, that does not survive. And if you think about what that pattern was, really think about it, it is staggering. 25,000 different types of protein, each one folded into a precise shape. Billions of cells, each containing 2 meters of DNA, coiled and packed into a nucleus, a few millionths of a meter across. Neurons wired together in networks of trillions of connections, forming the physical basis of memories and personality and consciousness. All of it built from the same handful of elements that make up rocks and seawater and air. Carbon, hydrogen, oxygen, nitrogen, calcium, phosphorus. Simple ingredients, unfathomable recipe. And understanding that distinction, truly feeling the weight of it, between matter that endures forever and patterns that flicker for a moment, that is understanding something important about what it means to be a physical thing in a physical universe. The atoms do not care. They carry no memory of where they have been. A carbon atom does not know it was once part of a thought. An oxygen atom does not remember helping to carry a signal through a nerve. They are just atoms. A carbon atom is 6 protons, 6 neutrons, 6 electrons, identical to every other carbon, 12 atom in the cosmos. What was special was never the atoms. It was what they were doing together, the arrangement, the organization, the astonishing, temporary collaboration of matter that could look around and wonder what it was made of. So light a candle sometime, watch it burn, see the wax shrink and vanish. Know that you are watching atoms change partners, carbon becoming carbon dioxide, hydrogen becoming water, and the flame is the visible evidence of stored energy being released as atoms settle into lower, more comfortable arrangements. And know that the same process scaled up and applied to the specific collection of atoms that made up a person is what cremation is. There is nothing supernatural about any of it, and nothing diminished either. The physics is complete. The accounting is exact. And the facts, once you really absorb them, are more astonishing than any myth could be. That you were assembled from the debris of dead stars. That every atom in you has a history that dwarfs the span of human civilization. That fire is just a rearrangement, not an ending. That the matter continues endlessly, while the patterns come and go like ripples on a pond. The atoms were never yours, you were just the most extraordinary thing they ever got to do together. If you have ever stared at a fire and wondered where the material goes, tell me about the moment that question first nagged at you. I would love to hear it.